Hello everyone. Today we shall try to discuss and learn about Henry's law. So, before discussing Henry's law, let us consider a system where we can see the solubility of a gas in a liquid solvent. Solubility of a gas in a liquid solvent. That is, we will see how can we make a gas soluble in a particular liquid solvent. So in this system, if we observe carefully, we can see there is a formation of two phases. One is the solution phase and the upper part is the gaseous phase at a particular pressure and temperature. So this system, let us say they are already in equilibrium. That is, the rate of evaporation and the rate of dissolution is almost equal or is exactly equal. That is, they are at equilibrium. Now, let us try to increase the pressure in this region. If we slowly try to create pressure over the gaseous phase, then what can we observe? We can see the volume will decrease, isn't it? The volume will decrease and more number of gaseous molecules in this region, that is per unit volume, will increase. Since pressure is more, volume decreases. So more number of gaseous molecules will accumulate here and slowly they will try to strike over the liquid surface of the solution phase. And after that, what they will do? They will try to enter into the solution phase. So this way, what can we observe? We can see more number of gas molecules will get dissolved into this phase. In other words, we can say more gas molecules will dissolve into the liquid solvent. That is, the solubility will rise or increase. Solubility will increase. So this idea or the phenomenon was explained by whom? It was explained by Sir Henry. According to Sir Henry, we can say the mass of the dissolved gas in a particular liquid solvent, increases with increase in pressure at a particular temperature. This was given by Sir Henry. So the mass of the dissolved gas in a liquid solvent can also be considered as the solubility, isn't it? We can also consider it as the solubility of the gas in that particular liquid solvent. So solubility of the gas in a particular liquid solvent increases with increase in pressure. So mathematically, how can we express it? Mathematically, according to Sir Henry, we can say the solubility can be expressed in terms of mole fraction, which is represented by small x, and let's say A. We can assign for any gas, for example, carbon dioxide or H2S. So we can write it like this: X is proportional to T. That is, solubility increases with rising pressure. Now, since this is proportional, so there must be a proportionality constant. And let's assign it as XA equal to K dash P. Let's assign it as equation number 1. So what does it indicate? XA increases with P, and this is the constant. So K dash is such a constant which depend on the nature of the solute as well as solvent. That is, nature of the gas and the nature of the solvent. This is an experimental result. If we consider the case of nitrogen gas at a particular temperature, say for example, let's say the temperature is 298 Kelvin and pressure, let's say 0.78 bar. So solubility, we can say it was found experimentally 5.3 into 10 to the power minus 3. Now somehow, if we increase the pressure, let's make the pressure double. It is an experimental result. If we double it, so we can see if we increase the pressure, then solubility also increases. So here we can write in this way. So it indicates that pressure proportional to the solubility. Here it indicates that since we double the pressure, then mole fraction also increases. That is, the solubility also increases. So this is just an experimental result of Sir Henry's law. I hope it's clear to everybody. Now we can rearrange this equation. How? If we bring it here, P equal to XA by K dash, or also we can write P equal to 1 by K dash into XA. Also we can write P equal to KH into XA. So KH, what is KH now? KH is the Henry's law constant. Since this phenomenon was discovered by Sir Henry, so according to him, he formulated a constant that is known as KH. And this constant is very important to measure the solubility. From this equation only we can see here, if we rearrange it, we get it as KH equal to P by X. Also, if you want, we can write A, P by XA. So, what does it indicate? It indicates that higher the value of KH for any gas, then solubility will be very low. Solubility will be very low because it indicates that these two are inversely proportional to each other. So, we will come to this point also. Now, if we look at this equation, let's assign this equation as equation number 2. So it seems to be as the equation of a straight line. So if we want to draw a graph, we can see if we draw a graph where we can put the pressure for a particular gas along with the mole fraction, then we can see it will give us a straight line. Since we have plotted the P on ordinates and the mole fraction in abscissa, we can see y equal to mx plus c. See, c is 0, intercept is 0. Obviously, this is an equation of straight line and the slope will pass through the origin, which indicates h. So this is the graphical representation and this is the equation of Henry. Fine. So this is the graphical representation for us. So let's discuss this point once again. KH is equal to P by X. What does it indicate? Indicates that higher the value of KH, lower will be the solubility. So if we consider any two gases, for example, okay, let's assign as X and Y. Fine. And let's say the value of KH at a particular temperature. Suppose, okay, let's assign here KH. Suppose this value at a particular temperature, for example, let's say 303 Kelvin. This is 78.2 and this is 34.1. Let us say, suppose, for any two gases. Now, at this particular temperature, if we look at the value of KH and if it is asked at this particular temperature, out of these two gases, which will be more soluble at this particular temperature, then what we have to do? We need to look at the value of KH which is given to us. So if we look at the KH value for X, that is given as 78.2. What about Y? It is given as 34.1. So from this equation, let's assign this question number 3. So from this equation, what we have understood? Higher the value of KH, lower is the solubility. So here, which value is more? This value is more. So obviously, the solubility of this gas will be low. At that particular temperature. So this is the correlation between the mole fraction, that is the solubility of a gas, and KH value according to Sir Henry. I hope this is clear to everybody. Now, this KH value is very much applicable for us. For example, if we consider the aquatic species if we consider, they feel more comfortable in cold water than warm water. How is it possible? So for that we need to know one more important point, that is what? This kh value. This kh value, it depends on temperature also. As we have come to know, kh depends on the pressure. It is correlated with the mole fraction. Also, kh value depends on the temperature. With rise in temperature, the kh value increases. With rise in temperature, kh value increases. That is, kh value increases with increase in temperature. Increases with increase in temperature. Increase in temperature. Now, the point of discussion is that aquatic species feel more comfortable in cold water than warm water. So the point is that cold water and warm water. Warm water. So since in cold water, obviously the temperature is low in comparison to the warm water. So if temperature is low, then kh value will also be low, and if temperature is more, kh value will be high, isn't it? High kh value, low kh value, low kh value, high kh value, fine. And what we have come to know from this equation, higher the value of kh, lower is the solubility. So in warm water, solubility is low, and in cold water, solubility is high. So if solubility is high in cold water, that is, the amount of oxygen will be available in cold water. That's why aquatic species feel more comfortable in cold water than warm water. So this is an experimental result, and these all are correlated with each other, and this is the main function of Henry's law. I hope it's clear to everybody. So in our next video we will discuss a new topic associated with Henry's law. Thank you very much for today.